The topic of my presentation is precise orbit determination of GNSS satellites based on combined microwave and SLR observations. My name is Krzysztof Sośnica and I would like to acknowledge the contribution of my co-authors Grzegorz Bury, Radosław Zajdel and Dariusz Strugarek. In this talk, I would like to address several issues related to the precise orbit determination of GNSS satellites on the example of Galileo satellites. I will start with the empirical models and the a priori boxwing models for Galileo. Then I will discuss the combination of satellite laser ranging data and microwave GNSS observations to improve the GNSS orbits. Then I will discuss the quality of the experimental IGS combined multi-GNSS orbits, and finally I will show the impact of orbit modeling on global geodetic parameters such as the Earth rotation parameters, geocenter motion, and the systematic effects that can be distinguished in the time series of these parameters. I will start with the Galileo orbit modeling, the analytical, empirical, and hybrid models. Already 3 years ago, metadata with the surface properties for Galileo satellites have been released, and based on the information retrieved from the metadata, we can construct the a priori models, orbit models for Galileo satellites. Why is it so important? The major perturbing force acting on GNSS satellites is related to the direct or indirect solar radiation pressure. And these perturbations are typically decomposed along 3 axes. So the d-axis pointing from the satellite towards the sun, y-axis along the solar panels, and the b-axis that is perpendicular to these 2 axis and forms the orthogonal right-handed reference frame. Also, the accelerations are shown by using the beta angle, so the elevation of the sun above the orbital plane, and delta U, which is the argument of latitude of a satellite with respect to the position of the sun. If we look at the accelerations decomposed into the d direction and the b direction for GPS from Block 2F and Galileo Fourier operational capability satellite, we see that especially for the b direction, the accelerations acting on Galileo have much larger variations than in case of the GPS satellite because of the elongated size of the satellite bus for Galileo. Simple models could be applied and were sufficient for GPS satellites, simple empirical models, whereas for Galileo the orbit modeling is becoming more complicated. So we use to extend the empirical models, which means that we have to estimate a larger number of parameters, or we have to use the a priori models that take into account the orbit perturbations in the better way. Surface properties were also published for other systems like QZSS and BeiDou, and we have also approximated values for GPS and GLONASS. So for other systems we can also construct the a priori models. Metadata from Galileo can be used to account for the direct solar radiation pressure and albedo. With some limitations, we can also model the antenna thrust, but these are based on the empirical values from measurements or estimates. And with some limits, we can also account for the infrared Earth radiation pressure, but the surface properties of Galileo satellites are not given for the infrared. We can also model to some extent the impact of the radiators. The radiators installed on the Y side of the satellite bus are easy to model just by estimating a Y bias, whereas the radiators on the X and Z sides are much more difficult to model, because if we estimate them as free parameters, then these parameters are strongly correlated with other parameters of our interest. What is the hybrid solution strategy? In a classical approach, we estimate empirical accelerations in the d, y, and b directions. In the classical ECOM model, the once per revolution terms were estimated only in the b direction. In the ECOM2, so the extended ECOM model, typically we estimate twice per revolution parameters in the d direction as well. Using satellite metadata, we can construct the analytical box-wing model, so we can estimate what are the accelerations acting on the satellite bus and the solar panels if we have information about the absorptions, reflections, and dispersion of all satellite surfaces. So we can combine these two. So if we use the analytical a priori box-wing model, we can reduce the number of estimated parameters. So we can, for instance, reduce the number of parameters by neglecting the twice per revolution terms, because they are typically strongly correlated with other parameters. Here we have the results of the SLR residuals from the classical ECOM1 solution and for Galileo IOF satellites, and we observe a lot of systematic effects in this solution. If we now turn the twice per revolution terms into d direction, so we switch from ECOM1 to ECOM2, most of the systematic effects are strongly reduced. However, we still have large systematics here for low beta angles for the satellites during the eclipsing seasons. If we use the a priori box-wing model and we estimate on the top of that set of empirical parameters consistent with ECOM1, most of the systematics are further reduced, especially for low beta angles, but for high beta angles we have large negative SLR residuals. As a result, box-wing removes most of the problems for low beta angles and reduces the number of parameters that have to be estimated, but the problem for high beta angles still remains. And how to handle this issue? We can use the combination of SLR and GNSS observations. First of all, the number of SLR observations is much lower than that in terms of the GNSS observations. The network is sparse. Only a subset of the ILRS station observe Galileo satellites, and one satellite can be observed at one time by the SLR station, and SLR observations are limited by the weather conditions, and the satellites can be tracked only during the cloudless skies. Nevertheless, SLR provides independent range measurements that are free of many systematic effects, such as the wet tropospheric delays or the ionospheric delays. How to combine both techniques? Here we have the starting point, so the microwave observations that uses only phase GNSS observations, which are characterized by the standard deviation of 1.5 millimeters. We have the combination with the first weighting strategy from the SLR validations coming from the best SLR stations and Galileo satellites. We know that the standard deviation of these observations is at the level of 15 millimeters. So we have ratio 1 to 10 between GNSS and SLR observations. Then we use different weighting strategies W2 because the number of SLR observations is much lower than that of GNSS observations. So we tested also the ratio 1 to 4 and the third weighting strategy W3 when we treat both type of observations in an equal way. So the ratio is 1 to 1. When we combine two types of observations, GNSS and SLR, we have to keep in mind that all possible models have to be fully consistent. So we need to use the same orbit modeling, we used the tidal modeling and so on. Only the models that are specific for different techniques such as troposphere delay can be different in both techniques. And what is the advantage of the combination between SLR and GNSS? First of all, if we look at the formal errors of the semi-major axis, if we have just 20 observations, SLR observations within one day, and we use the weighting strategy W3, we can improve the formal error of the semi-major axis by more than 20%. If we use different weighting strategies, the improvement is smaller. Nevertheless, we can improve the formal error of the semi-major axis. And what about the accuracy of the orbits? We can use the SLR validation. Despite this, SLR validation is not fully independent. However, for different weighting strategies, we see an improvement with respect to the M1 approach that uses only microwave observations. So for microwave observations, if we count how many SLR residuals are better than 2 centimeters, we will obtain the level of 61%. If we use SLR observations and the weighting 2 strategies for the combination, more than 71% of observations are better than 2 centimeters. However, for weighting 3 strategy, if we treat both observation types in an equal way, we observe a small degradation with respect to the W2 weighting strategy. So on the basis of this experiment and a series of other experiments, we concluded that this weighting strategy W2 with a ratio 1 to 4 is the best for the combination between SLR and GNSS. Here we have the slide we saw already before, and we saw these issues for high beta angles, and what is the result when we combine now the GNSS and SLR observations. We see that most of these issues for high beta angles are strongly reduced. We have here a slightly longer time series of observations. This is why this figure is a little bit denser than the figures in the top of the slide. As a result, if we take all observations, the standard deviation of SLR residuals is at the level of 25 millimeters in the combination of microwave observations when using a priori box-wing model, when estimating ECOM1 parameters, and using SLR observations. The SLR plus GNSS combination improves the orbits, but there is still room for improvement in terms of the SLR signature effect because of the large size of the retroreflector, range biases and troposphere biases in SLR solutions, and the network constraining of two independent networks, because we have SLR stations, we have GNSS stations. GNSS solutions are based on double differences, so we have a network solution. In terms of SLR, each station is treated more or less independently, so we need to somehow constrain the combined network or two independent networks to retrieve in a proper way the original orientation, the scale of the reference frame, and to obtain high quality orbits. Now I would like to address the issue of IGS experimental multi-GNSS orbits. The classical IGS products include just GPS and GLONASS orbits and clocks, and since 2019 we have also the experimental combinations based on multi-GNSS orbits, which include BeiDou, Galileo, and QZSS. If we run the SLR validation of these orbits, we can find several issues which are included in the combined orbits, even if the combined orbits are more robust than the single solutions. For instance, the GLONASS M Plus satellites show slightly different residuals than GLONASS M. The GLONASS M Plus residuals are shifted by 30 millimeters, which means that the construction of the satellite is slightly different, and we have some more differences in terms of this additional signal broadcasted by GLONASS M Plus. The SLR residuals for GLONASS K are very small despite the large size of the retroreflector on board GLONASS K satellite. We see still some systematic effects for Galileo satellites, FOC and IOF. We also find different patterns for BeiDou 3 CAST and SECM satellites. For BeiDou CAST, in this area we have positive residuals. Here we have negative residuals, which means that the satellite buses have to be elongated in opposite sides because BeiDou 3 SECM are very similar to Galileo residuals, whereas BeiDou 3 CAS are more similar to GLONASS M satellites, and these satellites are the satellite buses are elongated in opposite directions. Now I would like to address the impact of the orbit modeling issues on the estimated geodetic parameters. The geocenter motion, especially the Z component, are most sensitive to the all orbit modeling issues in GNSS. Here we have the time series of the Z component derived from GPS, GLONASS and Galileo solutions when using different models. And in principle we have different signals when we change the orbit model, different signals in the time series of this estimate. Here we have one empirical approach. This is the approach based on ECOM2. We have the a priori box-wing model and the set of ECOM1 parameters, and the a priori box-wing model and just three accelerations in three different orbital directions. For GLONASS, for these two solutions, the vertical scale is different both for the time series as well as for the spectrum analysis, which is given on the right hand side of this figure. From all solutions we can reconstruct the annual signal, but most of the solutions show also the harmonics of the Dragonitic year. Especially for GLONASS solutions we have a large peak around the third harmonic of the Dragonitic year. When does it happen? It happens when two orbital planes have the same beta angle, which means that the orientation of two orbital planes is exactly the same with respect to the Sun, and the third orbital plane has maximum of minimum value of the beta angle. Then we observe an excursion of the geocenter motion. For the satellite system that include just three orbital planes, we have this effect of the 1/3 of the Dragonitic year. For Galileo, this effect is smaller, much smaller than for GLONASS. Nevertheless, we see that the best solutions without this peak are obtained for the a priori Boxung model with the simple set of the ECOM1 parameters, or even without any periodical parameters that are estimated. What is the contribution of these two Galileo satellites in eccentric orbits? Here we have the formal errors of the z component of geocenter motion from the solution ECOM2 from the whole Galileo constellation and the Galileo constellation with when excluding two Galileo satellites in eccentric orbits. When we use these two satellites, so in this green solution, the formal errors do not exceed the level of 5 millimeters, whereas when we exclude these satellites, the formal errors may even exceed the level of 10 millimeters. If we analyze the time series of these estimates, we see that we can further reduce the third harmonic and the seventh harmonic of the Dragonitic year when we use these two satellites, which form the fourth additional orbital plane in the Galileo system. Now let's have a look at the time series of the polar motion coordinates. Here we have the spectrum analysis of the differences of the polar motion estimates with respect to the IRS-CO4 series for the GPS solutions, GLONASS solutions, Galileo solutions, Galileo solutions which uses the a priori Boxung model, and the combined solution based on GPS, GLONASS and Galileo. These solutions use just the empirical model, and we observe here in a similar way as we saw before in the geocenter time series, the harmonics of the Dragonitic year, and also we have some orbital resonances in the spectrum analysis of the estimated differences. For Galileo, we typically find the 2.1 days, 3.4 days and 10 days resonances between Earth rotation and satellite revolution periods. For GLONASS, these are 2.6 days, 3.9 days and 7.9 days. In the time series of the length of day estimates, we have in addition aliasing issues with sub-daily Earth rotation tidal models, and these are visible for all solutions independent on the satellite techniques around the days 14-15. And if we accumulate now the length of day values, so we end up with the minus UT values, we see that the GPS solutions have very large secular drifts because of the strong resonance between the Earth rotation and the satellite revolution period. Other satellite systems such as Galileo or GLONASS have much smaller secular drifts of the accumulated LOD values, whereas the combination is somewhere in between because the GPS solution still dominates the whole combination. To sum up, the best orbit modeling is based on the a priori box-wing model with 5 parameter ECOM. Adding SLR observations reduces the formal errors of the semi-major axis and removes the systematic errors for the Galileo in-orbit validation and high beta angles. The best relative weights for SLR and GNSS is 1:4. Secular drift of the accumulated length of day is much smaller for Galileo and GLONASS than for GPS solutions. Galileo-based geocenter is much better than the GLONASS-based geocenter motion despite 3 orbital planes in both systems, because Galileo satellites in eccentric orbits form the form orbital plane and improve the Galileo-derived geocenter motion, especially when using ECOM2 model. 3 main error sources can be identified in GNSS-derived Earth rotation parameters and geocenter motion, and these are related to orbit modeling issues. We have harmonics of the Dragonite gear, resonances of the Earth rotation and the revolution period of the constellations, and aliasing with sub-daily Earth rotation tidal models that are common for all GNSS systems. Thank you for your attention.